In this video, we're going to talk about conditional probability. So we first need to talk about the notation that's used to describe conditional probability. Conditional probability means that you're calculating the probability of some event given that some other event has already occurred. So the notation that we use introduces this vertical line here. And that vertical line just separates the event that you're calculating the probability of and the event that you're assuming has already occurred. So the way we would read this statement would just be the probability of event A given the occurrence of event B. So B is the event that has occurred. Oops, stylus isn't working again. Here we go. So B has occurred. And A is what we're trying to find the probability of. Okay, well that's lovely, but what can we do with that? Well, this comes back to the multiplication rule that we talked about a few videos ago. And originally we said that if we wanted to calculate the probability of the intersection of two events A and B, we could find that probability by simply multiplying the two individual events together. But that only worked if we had independent events. Remember, that meant that the probability of event A had no impact on the probability of event B occurring. But of course, events aren't always independent. So we can actually use this idea of conditional probability to give us a general multiplication rule that will work for any two events, whether they are independent or not. And this general rule says that the probability of the intersection of events A and B, again that's the probability that both events occur, is the probability that event A occurs times the probability of event B occurring given that event A has already occurred. So hopefully you can see the parallels between the two rules, the first for independent events and the second being the general rule for any two events. They both have this probability of A in them. What's different about the two equations is that instead of just multiplying by the probability of event B, as we did originally, we now have to multiply by the conditional probability that event B has occurred given that event A has occurred. So let's do an example. Let's suppose that we have that fun bag of marbles again. This time we've got 6 red marbles and 3 blue marbles in our bag. We're going to call event A the situation that we draw a red marble, and event B is the situation that we draw a blue marble. So if we want to calculate that the event, the intersection of A and B occurs, meaning that we draw a red marble and then we draw a blue marble, well then to get that we would take the probability of event A occurring, and we're going to multiply that by the probability that event B occurs given that event A has occurred. So let's go ahead and calculate that. Well, if we've got 6 red marbles and 3 blue marbles in our bag, that means we have 9 total marbles to begin with. And also we're going to assume that we're not replacing anything here. Should have mentioned that before. So first of all, we need to calculate the probability that we draw a red marble on the first draw. Where if there are 6 red marbles out of 9 total marbles, then the probability of drawing a red marble is 6/9. Then we need to figure out the conditional probability that event B occurs given that event A has occurred. Well, if we want the probability that event B is occurring, and remember that means that we're drawing a blue, there are 3 blue marbles still to choose from. But now, because we aren't replacing the original red marble that we chose, there are now only 8 marbles remaining. And so now we are going to need to simplify this. Let's see, we've got, this is 2/3. So if we multiply these together, we get 6/24. Oh, I guess I could have reduced that there. And so this is actually 1/4. So the probability that both event A and B occur is 1/4. We also need to talk about a formula that specifically gives us a way to calculate a conditional probability. And the formula is shown on the slide you see now. It reads, the probability of event B, given that event A has occurred, is the probability that both A and B occur divided by the probability of event A occurring. Now this might look kind of complicated, but it's actually just the formula that we were using earlier, only it's been rearranged. So I'm going to go back a couple slides for just a moment. Down here at the bottom of our slide we had the general multiplication rule that we were talking about. And we said that the probability of event A and B occurring is the probability of event A occurring times the conditional probability of event B occurring given that A occurs. The equation that I just showed you on the last slide is simply this equation right here, only we have rearranged it and solved for that conditional probability on the right side. And the way that we've solved for that is we divided both sides of this equation by the probability of event A occurring. And just like with any algebraic equation, when you divide both sides of the equation by the probability of A, they cancel out on the right side of the equation, and that's where the left side of the equation comes from, the probability of the intersection of events A and B divided by the probability of event A. So this is a formula that you do want to commit to memory and be familiar with. And let's do an example with it. Let's say that a group of people have been surveyed about their periodical reading habits. And there were two things that we were interested in. Event A is whether or not the person reads the New York Times, and event B is the event that the person reads USA Today. And you can see the results of this poll in the Venn diagram shown. 35% of the people polled only read the New York Times. 5% of them read both the New York Times and USA Today. 20% only reads USA Today. And then we haven't explicitly shown this in any of our videos before, but notice out here on the side it says 0.4, and that means that 40% of the people polled read neither the New York Times or USA Today. And you can get that simply by adding up the sum of these probabilities. So 35 plus 5 plus 20 is 60. And we know that the sum of all the probabilities of all the possible situations has to be 1. And so we got this 0.4 here by taking 100% and subtracting the 60% that we already had, and that gives us 0.4. Alright, so the question that we want to answer is, what is the probability that someone who reads USA Today also reads the New York Times? So let's go back to the formula that we just talked about, which said that the probability of event B occurring, given that event A has occurred, is equal to the probability, having issues again, of event, sorry, technical issues. It's the probability of event A and B occurring divided by the probability of event A occurring. And really this is what we're looking at. We're trying to calculate a conditional probability. We want to know the probability that someone who reads USA Today also reads the New York Times. So given that they read the New York Times, what is the probability that they also read USA Today? We can rephrase it that way so that we understand that this actually is a conditional probability situation. So we need to fill in this information here. What is the probability that both A and B have occurred? That means what is the probability that a person both reads the New York Times and USA Today? Well, we can see from our Venn diagram that overlap occurs 5% of the time. So the probability of event A and B is 0.05. And then we need to divide this by the probability of event A, which of course means that we need to include the sum of all of the regions in event B, or event A, excuse me. So that means we need to add 35% and 5%. So the probability of event A occurring is then 40%. So when we reduce this, we have, the probability of event A and B occurring is 5%. The probability of event A alone occurring is 40%. You reduce that and you get a probability of 12.5%. So that means that given that a randomly chosen person reads the New York Times, 12.5% of them will also read USA Today.